One of the big mistakes made in the dietary field is to think of glycine as non-essential. So glycine is your body's natural anti-inflammatory. That's a very interesting story, treating dental implants to keep them clean from gum infection. They actually have micronized glycine powder. If it's making a mess in your gums and teeth, we may be doing the same thing with blood circulation. The glycine is your body's natural blood thinner.
Or what we think we need isn't based on the full potential of glycine, as we'll get into.
Well, what's enough?
Glycine, D-Glycine,
Ah,
forms of glycine. What do you think about that?
yeah, I think about it as that's what happens when a little bit of ignorance comes in.
Ooh.
You know, I don't know. Some of the answers, we'll still find them out with future research, but
That's
it is
fascinating.
just amazing how universal and fundamental glycine is as a nutrient. And it's not necessarily just inflammation, just to let you go to sleep at night, right?
Yeah, oh,
Yes, it's the same glycine receptor.
so allergies, autoimmune disease, asthma. What are some of the big inflammatory conditions that you've seen maybe improve with glycine supplementation?
Oh,
Before we get
well,
into
I learned a
specific
lot.
ones? Welcome, everyone. This is going to be an amazing podcast with a world-renowned biochemist and expert, Dr. Joel Brind. This is part 2 to a glycine podcast that we did before. Glycine is this amazing amino acid that many of us, I would say almost all of us, are deficient in because the rates are what we think we need isn't based on the full potential of glycine, as we'll get into. So you could be aging more quickly. You could have out of control inflammation. You might not be sleeping as well. Your risk for cardiovascular disease and metabolic issues might be higher than they need to be. So today we're going to break down at least 10 different reasons you might want to start paying attention to your glycine intake, how to do it, where you can get it, and then we're also going to answer some of your very insightful questions from the previous podcast. So welcome, Dr. Brind. Thank you for joining me for this part 2. I'm really excited.
Thanks for the follow-up. Great to be here with you again.
Thanks. Okay, so tell everybody, just a quick intro to you, Dr. Brind. How did you get so interested in glycine? I learned about your work when I had your book, The Glycine Miracle, which I
Okay.
told them before I read twice. It was one of the best books I've ever read, one of the most understandable books, and I think one of the most impactful health books you can read. So what led you to writing that book? And
I was doing research as I've been doing. Just to tell you, I've been a professional researcher for something like 53 years. And at the time, I was working as a consultant, a consulting biochemist to a research foundation who was doing work on longevity. And they came upon a finding of if they fed laboratory rodents, rats and mice, a diet that was almost deficient in the amino acid methionine, not talking about glycine yet, methionine. People may know that from methylators and so on. Methionine is known to be an essential amino acid. But if you feed just barely enough for these rats and mice to survive, they will actually live 30 to 40% longer. So this was a very big deal. This was back in the 90s, 1990s. And it was reproduced by many other labs. It's now, quote, a thing that there's something called a methionine restriction, which is not still totally understood. Which, if you restrict the amount of methionine, you let the animals just eat as much as they want, the food just has a barely enough methionine in it to sustain their normal function, and they will live longer. One of the things I was asked to do is to figure out why. So what I was trying to do was actually come up with some kind of dietary formula to mimic methionine restriction. What can we put in that's actually going to help get rid of excess methionine? And it turns out that the amino acid glycine is the body's way of getting rid of excess methionine. Now, wait a minute. Rewind. What do you mean excess methionine? This is an essential amino acid. Yes, it's essential. And because it's essential, your body has so many ways of recycling it, regenerating it, reusing it, that it really needs very little. So methionine, of all the amino acids, which are bulk nutrients, you need so many grams per day. For methionine, you only need maybe half a gram. 500 milligrams, you got plenty. Maybe 300 milligrams is better, right? We try to get the diet so that it'll look like you have 300. It turns out other researchers in the 90s had just established that the body, when it gets rid of when you have excess methionine, it gets rid of it through a particular pathway that uses up glycine. It's actually It's an enzyme called glycine N-methyltransferase, which is in fact the most abundant protein in human liver, is a protein that utilizes glycine to get rid of excess methionine, because methionine is so essential to methylations, DNA methylations, neurotransmitter methylations. Many people who know something about nutrition know that methionine is a very key nutrient. And your body has particular ways of dealing with it, and every biochemist student learns about the methionine cycle, how this is recharged, how methionine is recharged. In fact, these days in the modern United States of America, where you're going to McDonald's or you're going to some other place where you're eating those cheeseburgers every day, you're eating meat, fish, and poultry day in and day out 3 times a day, it's those muscle meats which are loaded with methionine. So in fact, our methionine cycle is usually not working right after we eat. In the hour or two after we eat that cheeseburger, our liver is busy getting rid of the methionine. And guess what? When it gets rid of the methionine, it uses up glycine. In fact, it needs 2 molecules of glycine to get rid of every excess molecule of methionine that you eat. So now, here we have the modern American diet. Compare that to our forebears, whether they came from another country or they were in the US some generations ago, when people didn't have that much to eat and they didn't waste anything. So they used to throw the bones in the soup. Now we throw the bones in the trash. So we eat the muscle meat, we cut the muscle off the bone, we eat the muscle meat, we throw the trash in the soup. Not only are we eating more and more methionine, which we have to get rid of, but the glycine is in the bones, because every 3rd amino acid in collagen, which is the protein component of bone or connective tissues also, is glycine. So that's about, by weight, it comes out about 25% by weight of collagen is glycine. So we're doing a double whammy. Where not only are we eating more muscle meats, more methionine, but we also are getting rid of that amino acid that we get otherwise from the bones and connective tissues that we use to get rid of it. So these days, we have an amino acid which was thought to be non-essential, which is really conditionally essential. And the general condition is that it's really essential, because in not only 2 ways, but 3 ways, because you know what? We eat more, so we have more methionine, but we throw away the glycine we need to get rid of it. And because we eat so much, we're all getting fat, right? So we get overweight. And guess what happens when you get overweight? Your liver makes less glycine.
Yeah.
So it's a triple whammy that the glycine levels, even though they're, quote, normal is a statistical term, it just means what everybody's got. Right. So what's normal is not necessarily healthy. And for glycine, it's certainly, excuse me, generally not the case in this day and age in this country. So we have an epidemic of what? All manner of chronic disease that's blamed on chronic inflammation.
Yes.
Really, what do we have? We have arthritis and diabetes and cancer and heart disease and all of these things that you see commercials for expensive medicines for, things that are based in chronic inflammation. And then on top of all that, people ask the wrong question about inflammation. They say, oh, inflammation, why do we have chronic inflammation? Inflammation is the body's first response. The cells that do inflammation, they're called macrophages. They're the body's first responders to infection or injury. So they come right around whenever there's infection or injury, which means cell death, and they clean up the mess. And then they, importantly, they have to secrete all kinds of poisons in order to be able to kill whatever microbe got into you before it kills you in the case of infection. And it turns out that these first responders don't always come out with guns blazing. And with guns blazing, inflammation. The cells that do inflammation, when they're out there just cleaning up after injury, cleaning up the mess, getting the tissue rebuilt, starting all of those signals for building new tissue, for tissue repair, that's not inflammation. But it's mistaken for inflammation. Why? Because inflammation always happens. Why? Because it turns out glycine is the body's own natural regulator of inflammation, and we don't have enough of it. So we get inflamed, or parts of our body get inflamed, when there's no infection. And that was probably, I would say, in all of the whole glycine story. And you read the book, The Glycine Miracle, right? You get it
Yeah.
on Amazon that I wrote. And what's the real discovery, the real aha discovery? This is the nugget of what's really crucially important, is that inflammation is not a natural response to injury.
Mm.
When I get injured, if there's no infection, I don't get inflammation. I found it out with self-experimentation, the hard way, literally.
Yeah. And you've told me, like
Yeah.
in the first podcast, you told your stories of getting
Right.
burned by the sun, but not having the
Not
subsequent.
having all this inflammation from the sunburn, or having the disability and pain from having a fall onto my tailbone onto a concrete floor.
And the
So,
concussion. And you told me about
yes.
your CRP levels through your life, which is,
Yes,
would
the
you say the
CRP,
best?
yeah, CRP is the general measure for inflammation. It's a more modern version of an old blood test that used to be called the SED rate, the erythrocyte sedimentation rate. You take some of your blood in a tube and where it can't clot, and the red cells will slowly settle. If you're really healthy, they'll settle so slowly, it almost never settles. Your blood is really stable. If you're ill, if you have any sort of level of inflammation, they really go down like a rock. They sediment very quickly because of a protein that your liver secretes called the C-reactive protein. And CRP levels, when you measure my CRP levels, they're a standard part of an ordinary lab test metabolic profile. My CRP levels are always the very bottom
Yeah.
because I'm not glycine deficient. And
Yeah. And you've
so,
been, how much have you been taking for how long? And then because you're the biochemist, before we get into the other
right.
applications, tell us, how does it do this with the macrophages? How does it keep these macrophages
Oh, yeah.
quiet? And how does it
Okay.
prevent the end stage of inflammation? Give us that story too, so that they can
Oh,
understand.
okay. The whole story of inflammation it's a whole defensive response, like it's a war. When the body starts an inflammatory response, it's war. So in war, you have all kinds of different levels of activation, and you have different kinds of armaments and different kinds of bullets and different kinds of missiles and ships and tanks and all of that. The same thing is true with the body. There are all kinds of cytokines. You may remember from the COVID pandemic, the cytokine storm that was killing everybody. Oh, everybody's dying from a cytokine storm that is happening in the lungs with this COVID pneumonia. And what is the cytokine storm? Cytokines are these chemicals, proteins mainly, and peptides, smaller molecules that are secreted, and some of them things like hydrogen peroxide that are secreted by these macrophages in order to kill whatever is coming in that's going to kill you. And if you have too much of it, it will ultimately kill you. The ultimate response against an infection, that really people who get really serious infections and ultimately succumb to it, they typically will have something called toxic shock syndrome, where all of these armaments, they go nuclear. They blow up and just fill the place with inside the body with these very toxic materials. And that's needed in cases of really bad infectious agents like anthrax, right? Which is fatal in a lot of cases. So the immune system's response to anthrax is like nuclear. It can kill you. Ebola, this kind of thing. So what is it that starts the inflammatory cascade? It's a cascade of different materials that build up and have different kinds of cells that they target and so on. And what is it that limits it? So what normally happens? First of all, these macrophages get activated into what I call rend mode, rend versus mend. Rend is really to tear things up, to start shooting up the place. And they will do that if they're provoked because they detect the signature of some kind of bacterium. Could be anthrax or something else. Just typically they use, forget there's something used experimentally with the cell wall polysaccharides, lipopolysaccharides that are characteristic of bacteria. If you put those in the presence of macrophages, the macrophages will react to them. They will go into rend mode. Technically, it's called M1, macrophage 1 mode, as opposed to macrophage 2, which is clean up the mess mode. And in that M1 mode, they will shoot up the place. They will actually develop something that looks like an artillery cannon and a shell that will literally explode, and the final thing of the nuclear reaction is like the cell will explode, releasing all of these toxins all over the place, and you get that in toxic shock, which is largely fatal. So the first reaction to put these cells into the rend mode requires an activation that is inhibited by glycine. That is, it's naturally regulated by glycine. How does that work? It's like an electrical switch. If you know anything about electricity, so you have a switch on the wall for the light in the room, right? And there's two wires connected to the switch, right? So one of them is hot and the other one is it's not connected, it's cold. So that means there's a voltage between the two poles of the switch when it's not closed, when the light isn't on. That's 120 volts, right? In the US, in the wall, it's 120 volts. When you close the switch, you turn the light on, what happens to the voltage? Now the poles are connected. The voltage between them is 0. Now the switch is on. So the switch has become depolarized. The voltage has gone from 120 to 0. In the case of your cells, they work that way too, not with 120 volts. We're not all electric eels or anything, or even higher than that, but with about 70 millivolts. 0.07 volts. So there is every cell that normally exists has a resting potential, usually around not only your nerve cells, but other cells too. They have a resting potential, a resting voltage of around 70 millivolts. And that's a resting voltage. If the cell is turned on, if something happens to turn the cell on, it becomes depolarized, the voltage becomes 0, and the cell gets activated. So what happens to do that? And first of all, what maintains that potential? You have more negative charges on the inside of a cell and more positive charges on the outside. That's just the way the cells are naturally balanced. More negative inside, more balanced on the outside. But through the ordinary business of going around like an amoeba or like a macrophage in the clean up the mess mode, phagocytizing, right? Amoeba like gobbling up damaged bits of cells and cells that are past their prime and all of that to clean up the damage from whatever injury has taken place. Naturally, ions which carry these charges will leak in and leak out. So mostly in the inside of the cell, it's a lot of potassium ions, or the positive ions, and on the outside of the cell, it's sodium ions. And because of the imbalance between the size and the charge, there is this net negative charge on the inside. So if that depolarization happens, because the leakage naturally happens, and there are ordinarily pumps going. If you think about like a boat on the sea, right? If you got yourself a seagoing yacht, and what do you got in the basement of the basement? In the bottom of the hull, you have a bilge pump, right? That's ordinarily always on to pump out water. Why? Because the ship is going around on the sea and it's getting tossed and turned, and its water is going to be splashing in all the time. And so you need to have a bilge pump going to always pump out the water. Well, the same is true with the cell, except there's always water inside and outside, but what's different are the ions. So you naturally are going to have sodium ions coming in and potassium ions leaking out. So you have pumps going all the time in the cell membrane that pump potassium in and sodium out, which keeps to maintain this gradient, this difference between the ions inside and outside. One of the things that keeps the ionic balance right is to allow chloride ions, which have a minus charge, to come in, because chloride is naturally very low on the inside and very high on the outside. So if you open up a little channel, guess what? Chloride will flow in. You don't have to pump it. It flows right in through these channels. And when chloride flows in, it increases the negative charge on the inside, which keeps the membrane polarized. It keeps the switch off. It's a trigger lock. It keeps the trigger from turning on, keeps the switch from going on. It turns out that these chloride channels are regulated by glycine. They're called glycine-gated chloride channels. They're gated, regulated by glycine, and they're also called the glycine receptor or the classical glycine receptor. It's the same one. It's important in the central nervous system, which is why another one of these reasons why glycine is so important in terms of sleep, calming your nervous system. But it's the same one that's in these macrophages of the immune system that will do inflammation if they become depolarized. So when there's enough glycine around, it keeps the chloride channels open for enough chloride to come in so that the cell doesn't get depolarized and inappropriately activated. What's enough?
Yeah, what's enough? That's what I was just going to say.
What's enough? Normal? Oh, my
No.
glycine's normal. It's 200 micromolar. Guess what? That's not enough.
So would most
The
people,
normal range, yeah, the normal range is like 150 to 400 micromolar. No, you need at least 500 to 1,000 micromolar is fine. If it's
Mhm.
more, it doesn't hurt you. It's almost open-ended at the top. So, glycine has to be at least around 500. Otherwise, your macrophages will get activated in the case of merely cellular injury and not infection. And then you will get inflammation. And why is it chronic? First of all, it's not appropriate. That's the thing to recognize. As I said before, the big discovery is that most of this chronic inflammation as a result of injury is not appropriate at all. And
Yeah.
when I say injury, you get micro injuries just from circulating blood, just from running on a treadmill, even low impact stuff. Just blood circulation is going to give you micro injuries, especially around branch points, where your
Ovulation.
carotid arteries come off to your head, where your coronary arteries come. High pressure, the arterial circulation is a very high pressure fluid system. And wherever there are branch points, high pressure branch points, you get turbulence. And wherever you get turbulence, you're going to get micro injuries. So what? If they just heal, that's normal, right? Yes, no problem. But if you're glycine deficient, you get inflammation.
And
And if you
how,
get inflammation, plaque formation at arterial branch points, leading to heart attacks, strokes, embolisms, all of these problems, which glycine actually prevents.
yeah. And we're going to get to that in a second. I want you to tell us, though, how would someone test for this? I know before you told us that you don't have enough glycine if you're becoming inflamed because you're injured. But if someone wanted to go about testing it, how would they do it?
You can go to a lab, you can get a regular lab test for glycine. It's called an ELISA.
Okay.
Lab tests are funny. They're called the lab tests for a lot of things are called ELISAs. They're immunoassays. They use the antibodies. And ELISA stands for enzyme linked immunosorbent assay. And they developed an ELISA because they used to use radioactivity to measure these things way back in the day. But now the word radioactive has become radioactive. So the old test that used to work this way was called IRMA, immunoradiometric assay. So we dumped IRMA for ELISA because IRMA was radioactive. I like to tell that story in college. The kids understand it.
And now you've been taking 8 grams of glycine for, I don't know, maybe
About
at
17
least.
years, yeah. 8, 10, 16 sometimes, some experimentation, but steadily, especially my own formulation, Sweetamine, I've been
Yeah.
taking for about 15 years.
And how do your levels measure? Have you had them tested
I
yourself?
know, I don't,
Never
I
tested
tested them way back when I worked in a lab, and that was easy to do. And so
Okay.
my levels were maintained at around 700 plus
Okay. Awesome.
micromolar.
Okay, perfect. And now I want to get into the conditions, but 60% of Americans have at least one chronic disease, many of them tied to inflammation. So allergies, autoimmune disease, asthma. What are some of the big inflammatory conditions that you've seen maybe improve with glycine supplementation
Oh,
before we get
well,
into
I learned a lot.
specific ones? Yeah.
Yeah, I learned from my own self-experimentation, obviously from injury, but I learned a lot just from starting the business, selling Sweetamine, and having customers post testimonials and say, wow, I was hoping this was going to help me with my aches and pains. And it really did help with but I don't have migraines anymore. I wasn't even taking it for that.
Yeah.
So you see, there are testimonials like that.
Oh, yeah.
Surprise, you were feeling a lot of effects of inflammation. And people say you should be very cautious with glycine because you don't want to take too much right away. And it's true, if you take too much and for some reason you don't agree with the free amino acid formulation of straight glycine, you might get a headache. You might get diarrhea even, very rare. But then it goes away, so you stop it. It doesn't hurt anybody. It's not, give a Snickers bar to somebody with a peanut allergy, it'll kill them.
And I think I've read about studies, yeah, and that's another thing we're going to get into in a second, but I've read studies where they actually put glycine straight into the bloodstream. You sent me
Oh, they
a film
do
about
that.
this.
Actually, this is done. If you really want to see the toxicity of glycine, people
Yes.
say, oh, you've fed rats or you've fed people so much and so much. Nobody ever gets fed as much as they get fed. There is a very common condition, benign prostatic hypertrophy or benign prostatic hyperplasia, the benign prostatic disease, which is the prostate swells up, it impairs urinary function. So a standard therapy for this is a surgical procedure called a TURP, a transurethral prostatectomy, which is like a roto-rooter kind of thing. It's a very crude procedure. You'd think it's, and what they do is while they're doing this very crude surgery, when I say crude, this surgery was perfected 100 years ago. They still do it.
Wow.
It still works. And it still works, gets rid of the excess tissue, and then it heals up very quickly. And they wonder why, you wonder why it heals quickly, because what they use to irrigate is, you can't irrigate with water because that's not the same ionic strength as blood. You got to have the right ionic strength of dissolved salts in it as blood. But you don't want to put in salt water. That really stings. So some years ago, some decades ago, they settled on using 2% glycine because it has the same osmotic strength
Mm.
as blood serum or plasma, but it doesn't sting. And so they use that. And you wonder why people get along so well, because get along after this surgery so well, recover so well, is because they actually irrigate the surgical site with 2% glycine. It floods the circulatory system with glycine, sometimes up to 100 times the normal value. You may, instead of one millimolar, 1,000 micromolar, you might get 100,000 micromolar, 100 times normal that. And it still doesn't do any permanent harm to anyone. You just let it wash out. It washes out of your system very quickly. So I would say, when people say, how much is too much? What's a toxic amount that is really poisonous? Actually, I don't think you can eat enough glycine and actually absorb enough glycine by eating it to cause yourself any real harm. That's how safe it is.
Yeah.
People, they will cite things in the literature. Oh, glycines, it's a risk, it's risky. And then you look at the literature and you see they injected IP into the chest cavity of rats. They injected 10 grams per kilogram of glycine or something, and they managed to kill a few rats. It's really unbelievably safe. That's why I feel I've been in business now for 17 years, and I don't worry about legal problems or anything like that, because I might worry about legal problems if I was selling peanuts.
Yeah. Yeah.
With
But you're
peanut
turning down
allergies and
that.
so on. But there's nothing in Sweetamine, my product there, that you could actually get allergic to. You may not agree with you to take glycine as the free amino acid I mentioned before, right? Collagen. So you can take it as gelatin or collagen peptides. If you take an enriched source of glycine in that way, bone broth, any of those very good 25% glycine, those require digestion, which means they don't get into your bloodstream right away. And for those people, occasionally people will get headaches, or they'll get diarrhea or some kind of digestive system symptoms. You can read this in WebMD. Say glycine, what are the side effects? They're all just transient. If for some reason you are intolerant, that is to say, taking the free amino acid straight up disagrees with you. And there's some people that it does, maybe 1 or 2% of people.
Yeah,
But
that's great. But yeah, go to food sources, lower
right.
the dose. So there's lots of ways. We're going to talk about all the ways.
Divide the doses, do whatever you want. So I tell people something. They say, I can't take your product because I don't like it sweet. Can you remove the sweetener? I say, no, glycine is naturally sweet.
Yeah.
It just has a bad aftertaste. So we modify a little, not chemically modify it, but we add just enough and formulate it just so it tastes a little more like sugar, all natural, but it's still going to be naturally sweet. I say we can't take the sweetness out of it. So you either have to take capsules, which is very impractical, or just take it in a form that requires digestion. So take it as gelatin or collagen peptides, which is really the same nutrient.
Yeah.
Or nowadays, everybody's big on magnesium, that they're selling you
Yeah.
magnesium glycinate.
Yes. I
See
was
that
gonna
all
say
over the
that.
place. Magnesium glycinate.
Yeah, you
Best
got to tell
source of
us.
magnesium, so absorbable. But do you know that, and they say, take these 2 big pills and you get your 300 milligram daily requirement of magnesium. And those 2 big, like horse pills that you have to take to get your 300 milligrams of magnesium, guess what? You're getting 2 grams of glycine, because magnesium glycinate is 86% glycine.
Okay, so every
So yeah, that's a good
formulation,
way to get it too.
is that consistent? 2 grams pretty much in every formulation? Is that kind of
Well,
standard?
1.5 to 2, depending on whether they say they're providing 200 milligrams or 300 milligrams.
Okay, I
They
love
say
that.
that's the minimum requirement for magnesium is 200 to 300 milligrams. And depending on what brand you get, they'll say our serving size will give you 200 milligrams or 300 milligrams. The 200 milligrams will give you 1.5 grams of glycine, and the 300 milligram will give you 2 grams of glycine.
Perfect. Thank you for
Bone
breaking
broth
that
gives
down.
you For every gram, you'll get a quarter gram of glycine.
Yeah, we have a bone broth too, like you said, or you can make yours own at home. And then I wanted to be clear about this too. Essential aminos, like if you're taking an essential amino acid supplement, that doesn't always mean that you're going to be getting glycine.
Oh, yes. See, classically,
Yeah.
one of the big mistakes made in the dietary field is to think of glycine as non-essential. They call it non-essential because your body can make it from scratch.
Yeah.
That is, when I say scratch, I mean your body can make glycine from carbon dioxide, ammonia, and formaldehyde. Your liver
Yeah.
makes it from that every day. So it's very fundamental material. You can get natural, you say, is it glycine natural organic? You can get natural glycine that's not organic because glycine is actually made in the inorganic environment. You can find it on meteors and comets and asteroids.
Yeah.
It's so fundamental. It's been around here for so much longer than living things have been around. It's a really almost like a salt. I consider glycine a bridge substance. It's inorganic and organic. It's organic, sure. It's one of the building blocks of proteins. It's an essential amino acid. But on the other hand, it's made inorganically all the time, just in the environment. And anyway, that's
I just wanted to say I have this
well,
essential amino
I'm sorry,
acid. Yeah.
we were talking about what do we mean by essential?
And then if you buy an essential amino acid supplement, that doesn't necessarily mean you're going to get glycine.
No,
either,
in fact,
classically,
classically, to make a very long-winded story short, in the classical lexicon of what is essential and what is non-essential, and they say that glycine is non-essential. If you take a formula that says gives you 100% perfect balance of your essential amino acids, it won't have any glycine in it because they don't think of it as essential. In fact, if you just take a mixture of essential amino acids and nothing else, it's actually going to strip glycine from your body, and you need to take more of it. Why?
I love that.
Because
Methionine?
remember the excess methionine? That you need glycine, 2 molecules of glycine to get rid of every 1 molecule of methionine. That's taken in excess. That's what your liver actually does. And so we found that out actually doing some longevity experiments with it. First thing I tried to do, we ran some experiments with rats and then with mice to try and simulate methionine restriction by feeding glycine. If we give the animals lots of glycine, that will help them clear their methionine and they'll live longer. Yes and no. Yes, it helped them live longer, but no, it didn't help them clear methionine because guess what? Their methionine levels didn't change one bit. But they live longer. Something else is going on. Yes, the something else that's going on is that methionine restriction is actually removing a source. The excess methionine is actually poisoning you by robbing you of glycine. That's how that's happening. So it's the glycine. It wasn't really so much the methionine. If you have excess methionine, your liver is going to get rid of it. There will always be enough glycine to get rid of excess methionine. And why do I say that? That gets into some of the different ways that glycine works are not all about its biochemistry. So glycine, biochemical, yes, it's important in making DNA, and it's important as a building block for proteins, and it's important in synthesizing other amino acids. But actually, when it works to stop inflammation, it's not acting in a biochemical way at all. As I said, it's a gate to this chloride channel. It's just a ligand, almost like a hormone, but something that operates that way. It operates a switch. It keeps the switch closed, keeps the switch open, which means off, right? Keeps the switch open so that you don't get excess or inappropriate inflammation. So it's in that sense, it needs to be, we talked about blood levels, and what my blood level was about 700. We talk about micromolar, which is a way of measuring things by the piece rather than by the gram.
Yeah.
So it's about half millimolar glycine or 500 micromolar glycine. Now, in order to make all the proteins that your body needs to make, and it needs glycine to make all of them because there's some glycine in every protein, and glycine is about the most abundant protein, most abundant amino acid that you have. If you have even 100 micromolar glycine, you have enough to make protein. So you see, it really is non-essential as a biochemical, as an amino acid. In terms of its biochemical building block function, you can't run out of glycine. Your body's going to make enough, but it's not going to make enough for its function which needs bulk amounts of glycine to be in the solution to act as a trigger lock to keep things from going haywire. And it's not necessarily just inflammation, just to let you go to sleep at night, right?
Yeah. Oh,
Yes, it's the same glycine receptor
yeah. We're going to
in
get
the
into
nervous
those.
system.
Yeah, I love that. We're going to go there. And I want to close this section really quick. And then we're going to go to those distinct, like sleep and cardiovascular. But I just wanted to say you can get glycine in plant products. It was something many of you mentioned, but the amounts are just a lot smaller. And so you, for instance, you could have a gram in a cup of soybeans or half a gram in a cup of lentils or chickpeas. You're just going to have to eat a ton to get to that 8 grams. That's what,
Yes, and
like
that's about it.
16
Soybeans
cups.
is about as high as it gets in the plant kingdom,
Yeah.
which is why the botanical name for soybeans is
GlyNAC.
glycine max.
Yeah, glycine max.
Yes, that's the max glycine you're going to get out of a plant is from glycine max, soybeans.
And you said that vegetarians, vegans typically have higher levels of glycine because they're not eating so many muscle meats. Do you think
Yes.
that's optimal? Or do you think we should be getting the meat-based nutrients and having meat, but also balancing it with glycine?
It's all about the amino acids. And people say the amino acid mix in animal foods is not as healthy. And animal meat eaters, they get more cancer, more heart disease, they die younger. Vegans live longer, they get less cancer, they get less heart disease. Wait a minute now. The trouble with this measure of animal protein is usually we throw away the glycine
Yeah.
because the collagen is not included. I would say you can eat a healthy and adequate diet if you are a vegan, and you can eat a healthy and adequate diet if you are an omnivore. Our body's designed to be, we're designed to be omnivores where we can eat everything, a good mix of things. And your body will do fine with any of them as long as you get the right mix. So if you're a vegan and you don't get enough glycine, you're not going to be optimally healthy. If you're a meat eater and you keep throwing the bones into the trash and not the soup and eating the glycine that you need, you're not going to be healthy. So it's a matter of getting complete proteins, which is the right balance of essential amino acids, but you can't forget the glycine, which is not ordinarily included in that mix.
Perfect. And then this last supplement I want to talk about, GlyNAC. I know you have some big thoughts on this, like GlyNAC.
I do, yeah.
2 recent trials have shown that it can improve many parameters of
Yes.
hallmarks of aging, gait speed, strength, mitochondrial function, all on and on. And it's a buzzword these days. So
GlyNAC.
GlyNAC, glycine, cysteine, tell us. Is
Okay, well, a
GlyNAC
couple of
better than-
scientists,
Yeah.
a couple of scientists, Doctors Kumar and Sekar, who are at Baylor University in Texas, who have been promoting this idea of GlyNAC. They call it the power of 3 because the big 3 there is a little tripeptide called glutathione, which is another buzzword, right? Glutathione, it's your body's key antioxidant. You know that if you don't have enough glutathione, a lot of things can go haywire, and that's true. And glutathione is it's a tripeptide. It's a little molecule made of just 3 amino acids, glutamic acid, cysteine, and glycine. The glutamic acid part is non-essential, and there's always an excess of that. The limiting ones, the ones that you might not have enough of, are cysteine and glycine. So they say if you take these 2 that are the limiting ones, glycine and cysteine, NAC is, by the way, an abbreviation for N-acetylcysteine, which is just the dietary form. It's cysteine. Okay, so it's GlyNAC is glycine and cysteine in supplement for 1:1 ratio. So if you take those 2 limiting components of glutathione, you'll have lots of glutathione, and they call this the power of 3 because glycine has great benefits, glutathione has great benefits, and cysteine has benefits because that's the key part that makes glutathione the antioxidant. That's the antioxidant part of glutathione. So there's a big literature that goes back far before these researchers, that goes back decades, a very big following of glutathione and how important that was. Interestingly, with the group that I was working with who established a methionine restriction as a way of increasing lifespan, we found that the animals who were methionine restricted, not only did they live longer, but their levels of glutathione were lower than the controls. So this made everything go tilt in the reasoning. And what I've concluded is that basically, yes, glutathione is important and it is a key antioxidant. And the more of this muscle meat that you eat, the more you're stressing your mitochondria, making them run hotter, that kind of thing. The more, like reactive oxygen species you have, the more antioxidation you need, the more glutathione you make. Because in fact, when your liver is processing that excess methionine and using up glycine, it's also going to be, as a byproduct, it's amazing how everything is so perfectly balanced. As a byproduct, your liver is going to make more glutathione. So the more oxidative stress there is, if everything is still working right, the more glutathione your liver is going to make. Glutathione is important, yes, it has to be understood in that way, that it's not always the absolute amount that you need. The other thing about glutathione is that, yes, the cysteine is just as important and it's limiting, but muscle meats have lots of cysteine. Cysteine's a sulfur-containing amino acid. It's made from methionine, and it's the antioxidant part, as I said. So when your liver gets rid of excess methionine, it's also generating more cysteine and more glutathione. So why would you necessarily need to take GlyNAC as a supplement if you have a diet that is providing an excess of muscle meats and excess of cysteine? So that's not likely to be limiting. So that's one question I have. The question I have scientifically about it is that in all of this research that I've been able to find about GlyNAC, they never test gly. They test glutathione, all three of them. They test cysteine, they test GlyNAC, but they've never shown supplementation studies with just glycine.
Why do you think that is?
I don't know. I think my hunch is that in some way they're stuck on glutathione. The other thing is they do find that people do take NAC, and it does have benefits. And another thing may also be the whole Tylenol business, which made the news lately, about somebody saying, if Trump says Tylenol's bad for you, I'm going to take a whole bottle, and then they end up dying from it. You can't overdose. You can overdose very easily on something like Tylenol because it's acetaminophen, also known as paracetamol. And acetaminophen is known to be toxic to the liver. How is it toxic to the liver? It specifically degrades glutathione. Specifically defuses the NAC part, the cysteine part of glutathione is oxidized by paracetamol, by Tylenol. So when you take Tylenol, you are naturally degrading glutathione. You're specifically targeting and poisoning your glutathione. So that may be one reason why people often are deficient in cysteine and they would need to take NAC. So what I say is, if you like Tylenol as a pain reliever, always take NAC with it.
I love that advice. And I'm wondering, if you were going to design the experiment to really parse out whether glycine alone could be as effective, what would you do? And then why do you think this hasn't been done in human clinical trials? Because there's a lot of animal evidence around glycine and some human, but why do you think that there hasn't been this development?
I don't know.
Yeah.
I would, I like your first question. If I were to do it, how would I do it? I have tested just glycine. People might ask me, why don't you test NAC? I'm not in a position to do that. I was working with the National Institute on Aging, and I had an occasion where I could test glycine on mice, and we had a very good result. A nice paper came out of that about 5 years, more than that now. Time passes.
Time flies.
Was it 2015 or 2016? I don't know. Within the last 10 years, anyway, we had a very nice paper came out in Aging Cell about glycine significantly extending the lifespan in mice. And that was done in 3 separate study centers simultaneously. The result is solid. And so that's what we did, but I don't have the occasion, the opportunity to test them. I suppose if I had a laboratory now, I would certainly want to reproduce the test with GlyNAC and compare them to glycine alone, NAC alone, and also glutathione. You do all the different parameters. It's just odd that this one parameter of glycine alone was missing. And who knows? There's always things to be discovered. And the last thing I'm going to do is say anything bad about GlyNAC supplementation, because that's very good for you. If you don't need the NAC, well, it's not going to hurt you.
Yeah.
It's a simple amino acid.
And it's something, sorry, go ahead.
Yeah, it's not going to hurt you. So I wouldn't object to that. It's just scientifically, I wonder why they didn't test everything individually.
Yeah, that's interesting. And maybe a daily intake of adequate glycine could prevent the need for it. I did try it out this week and I did sleep well, but I also eat a lot of
What?
glycine.
I can't read what's in the.
It's GlyNAC. I tried it
Oh,
out.
that's GlyNAC. Okay.
That's GlyNAC. I tried it out this week and I slept a lot longer than usual. I don't usually take supplemental glycine. I usually drink it and eat it. So that could be why. But it was interesting. I just love your thoughts on that. And I love how balanced you are. And I hope that study is eventually done. There was a study, a recent study in, I think, obesity around glycine. Do you want to start? Do you remember that study?
Oh, the International Journal of Obesity. Yeah, yeah.
Tell us about that
The
study.
last time I published in that journal was 1991. Good journal. I just haven't been publishing in that area. The that was about obese. When you are obese, your liver actually makes less glycine. They actually documented that. I think I mentioned that just in passing and earlier on in this discussion.
You did.
That it's one of those double, triple, quadruple whammies where you're short on glycine and short on glycine and short on glycine. There was a group, it was a Mayo Clinic group, and that was working at a Mayo Clinic in Minnesota and also in Jacksonville, Florida. They're working with kids who are obese kids because that's an epidemic now in kids too. And of course, heart disease is an epidemic, but it's not an epidemic in little kids. You don't find 8, 10, 12, 14-year-old kids dying of heart attacks. So the doctors, yes, they were Mayo Clinic doctors. What they were testing was a very interesting hypothesis. We have markers for heart disease among middle-aged and older people. We have LDL cholesterol and various other markers for heart disease. We're kids, we're a children's hospital. They were a children's hospital in that one in Jacksonville. They said, so we want to see if they have markers for heart disease. These obese kids, do they have markers for heart disease? And if they have markers for heart disease, maybe that would be predictive, right? This is a big deal in scientific research. If you can find something in the blood that's going to say, you know what, in 20 years, you're going to drop dead from a heart attack or likely to because you have too much of this. Therefore, you should change your diet or take this medicine or do whatever you need to do to normalize it. So they noticed in these kids that they have all of the markers, a lot of the markers for typical cardiovascular disease that they see in middle-aged and older people. And they don't have the disease, but they have the markers. And so they looked at the markers and what are the markers? One of the key markers turns out to be glycine, that the glycine is low. Why is the glycine low? Is it diet? Not so much diet in terms of not enough glycine in the diet, probably just too much food altogether in the diet because the kids are obese and obese kids, their liver makes less glycine. So now they're hypoglycemic growing up, which feeds into all the intravascular, the inflammation inside the blood vessels leading to atherosclerosis and plaques. And by the time they're in their 30s, a lot of them do die of heart disease or get significant heart disease. So that's how they looked at some of the markers, the molecular markers, the genetic markers, using a tool called genomics to see what genes are actually expressed in the blood of these kids. So they've done some very good research at this group. This is Mayo Clinic again with I forget which children's hospital it is in Jacksonville, Florida, but I like the work they do. Very foresightful, I guess. Very good, looking at some very interesting questions which are of great benefit and will be of great benefit, I think, to people's health. And underscoring the importance of glycine is one of the things that's come out of that.
Yeah. And in our last podcast, you said you were starting to be able to influence the cardiologists in your life or family. And are the mechanisms the same? Like in our blood vessels, is glycine working to turn down that inflammation in the same
yeah.
way?
Yes. And not only that, glycine works in several ways. Inflammation, you have an increase in one of your clotting factors that's made by the liver, I think factor 7, so that blood is more clottable that way. Glycine is also anticoagulant. There are some things now, it's a big deal to say different things. Make your platelets aggregate. Actually, glycine is your body's natural blood thinner.
Wow.
Because just on platelets, I'm not going to give any medical advice and say, oh, your doctor put you on clopidogrel, so you don't need that, just take glycine. Theoretically, it might work, but you can't medically predict these things, especially in individuals. But I would say that glycine, yes, is your body's natural blood thinner. It has the same glycine receptors on platelets. And instead of being a trigger lock to prevent them from causing inflammation, what it does to the platelets, it prevents aggregation, because the aggregation of platelets into a plug is one of the mechanisms by which your circulatory system plugs up holes and keeps you from bleeding to death from ordinary insults of daily living. It does that. So it inhibits platelet aggregation, keeps us naturally thin, your body's natural blood thinner. It inhibits the secretion, I think, by the liver of factor 7. I think that's the one. And also another particular one that's big in inflammation is that there is another protein that is secreted by platelets called PAI-1, PAI-1, platelet aggregation in, no, not platelet. It's secreted by plates. It's called plasminogen activator inhibitor 1. See, when your blood clots, when something happens, right, when there's a cut in one of your blood vessels, it secretes a little substances released from the injured tissue, which starts what's called the coagulation cascade. The cascade, because one enzyme activates another, that activates another, that activates another, in order to amplify the response, so that from a few little molecules, you can actually get milligram quantities of a platelet, of a fibrin plug that can plug up the hole, keep you from bleeding to death if you get seriously injured, that sort of thing. But at the same time, if there were just a coagulation cascade, every time you got a little cut, your whole circulatory system might clot, right?
Yeah.
Now you have this cascading system. What's going to stop it? At the same time that the coagulation system is activated, an anticoagulation system is also activated in the same spot. It's called the fibrinolytic cascade. And fibrin is clotted substance that turns your blood into jello, right? So it can't flow and plugs up a hole. There is also a fibrinolytic cascade, which ends up in dissolving clots. So you may have heard of, in heart attacks and strokes, they now use something called these clot-busting drugs. Plasminogen, I forget now what the name of it is, but these are kinases.
Oh, kind of.
Enzymes that work in that way, the clot-busting drugs that will act as fibrinolytic agents, which will dissolve clots. They will literally break them apart enzymatically. That is automatically activated whenever the clotting cascade is activated, so that you end up with the only place where the plug actually stays is in the hole in the wall.
Nice.
And that gets stabilized by another factor that is added by the wounded surface of the blood vessel. It's called fibrin stabilization factor. That stabilizes the clot, but you don't want a clot inside your circulatory system where the blood is supposed to be flowing. So the anticoagulation cascade, the ultimate enzyme there, which dissolves the clot, is called plasminogen. And I'm sorry, it's called plasmin. And plasminogen is the substance that's turned into plasmin right before it. So plasmin, the activator of plasminogen activates plasmin, but there is a plasminogen activator inhibitor, which will inhibit the dissolving of the clots. And that is all part of this very complex system, but it is increased in inflammation. When you have systemic inflammation, not only does your C-reactive protein go up, which is what we talked about earlier, that's a clinical test for whether there's a lot of inflammation. But one of the hallmarks of inflammation is that your PAI-1, your plasminogen activator inhibitor, goes up, which means your blood ultimately, between that and factor 7 and the platelets, if you have systemic inflammation, your blood is more clottable. So people end up with heart attacks and strokes, and what do? They put them on drugs like clopidogrel, and the names escape me at the moment of some of them. But if people are familiar with these blood thinners, the blood thinners typically block.
Warfarin, is that one?
What's that? Warfarin. Yeah, warfarin is another one of those. Warfarin it's a good rat poison. You know that's where that comes from. That was the rat poison. The way it works is rat poison is warfarin, they put it in the bait trap, and the rats eat it. And they start to bleed internally because it inhibits coagulation. So they go outside looking for water and die.
Oh, I did not know that.
That's how that works. So it's a
Yeah.
Sorry,
Great.
I don't know if you want to include that in the podcast, but that's just a little story about warfarin In a medically supervised proper dose, it extends lives for many years for people who otherwise have blood which is hypercoagulable. How do you know their blood is hypercoagulable? You had a heart attack. You had a
Right.
stroke. That was inappropriate coagulation. That's how we know.
Nice.
But again, those are blamed on chronic inflammation that leads to those conditions. And
Yeah. See,
glycine works against that.
that's
I'm not
amazing.
saying nobody's saying glycine, oh, it's a cure-all. It's just an essential nutrient. You have to have lots of different nutrients. Glycine's one of them that tends to be overlooked, and it's very key. It doesn't mean it's going to absolutely prevent anything.
No, and
Like,
this is, yeah,
But
not medical advice, but just like you
no,
say, an
that's
essential
right. But
nutrient.
it will help to keep things normal, doesn't
I
it?
love that. And I want to go through a few more because if you have time, because there's so many different
Oh, yeah, go
applications.
ahead.
One that I thought was particularly interesting along these lines, that it can be an antidote to the overconsumption of sugar and liver protective in that way. So are you familiar with that research?
Oh,
Can you talk
well, I
about
don't know about, not sure about the sugar part in terms of diabetes. If you're talking about becoming diabetic, which we tend to con tend to blame on the overconsumption of sugar, which has a lot to do with it, because you see, your body is really designed to deal with famine, not feast.
Yeah.
It's designed to manage to keep itself alive in the most meager circumstances where it can barely get enough of anything to rub two molecules together to generate energy or reproduce a cell. So your body's designed really to withstand famine, but not to withstand feast. For example, with sugar, the insulin pathway, insulin is a way of getting rid of sugar, burning it, storing it, turning it into fat, whatever you have to do with it. It's really just that insulin pathway. It's really just the only pathway there is. Whereas if you have too much of it. If you have too little of it, you have 7 ways till Sunday to regenerate sugar. Your body can make sugar. We got no sugar. Wait a minute. We need some sugar to run on. The brain can run on ketone bodies, and the muscles can run on fatty acids, and we still need some sugar. You still got to have some sugar, but you don't need to eat any. You can have a carbohydrate-free diet because it's non-essential. Your body can make sugar from almost anything. Any amino acid, your body can make sugar, including glycine. Your body can make sugar from it if it has to. It can make sugar from fat, a little of it, not that much, but it can make ketone bodies and it can make a little sugar. So in order to withstand starvation, your body has a lot of alternative pathways, a lot of redundancies built in, but not to get rid of it when you have too much. Same thing with methionine, muscle meats that we have so much of these days. There's really only one way to get rid of excess methionine, and that uses up glycine. There's no other pathway for it. But if you're short of methionine, oh, there's so many ways to regenerate it and recycle it and reuse it. And there's lots of different ways, which is why, even though essential, you need so little of it because your
Yeah.
body can do a lot with it. You get into these, I know a lot of people talk about methylation,
Yeah.
low methylators, for example. That's a very interesting story.
Yeah, tell us about that because I
Yeah.
do hear a lot about glycine and methylation, and there's
Yeah,
lots
and
of
you
buzzwords.
wonder because people, I think somebody even commented after the last podcast.
Yeah.
They said, well, isn't glycine bad if you're a low methylator? You need because glycine gets rid of methionine. Methionine is the key methylator. It's activated to form SAMe, which is the active form of methionine. That's the methylator. You need methylators because DNA bases need to be methylated variously to turn them on and to turn them off. Neurotransmitters need to have methyl groups added. These one carbon units are added universally by something called S-adenosyl methionine, which is the activated form of methionine, the essential amino acid. So you got to have it. Your body has lots of ways to reuse it.
And what does
Well, so what
methylation
happens?
do? Just tell
What
us, like,
happens when what's that?
yeah. What does methylation do, like at a very basic level for someone who might be new to the concept?
Methylation is just if you think of little ball and stick models of atoms and molecules, it's just a little like a little stick it's like a cog in the wheel. So it's a signal. So if your DNA is transcribing and translating, making all these proteins and making more DNA and going on about its business and doing that, and which genes are getting turned on, which genes are getting turned off. So it goes through, so on part of the DNA, there'll be this particular base will have a methyl group sticking out at one particular place. that gets bypassed. We don't make that protein. So methylation is one of the ways that the genome operates in order to using it as a switch to turn on or turn off or bypass certain genes, the translation of transcription, translation of certain genes. Transcription, I guess, at that level of DNA. So that's what a methyl group does. It's a physical other little stick, a little cog in the machinery that changes the shape of the molecule in order to exert a particular function informationally. It's interesting, like just like glycine at the cell surface, it comes down to being a switch. So this has a lot to do with switching in the copying of information in DNA. So the addition or subtraction of methyl groups. That's just one way methyl groups are important. They're important to make so many different things, hormones, neurotransmitters, because a methyl group is a one carbon unit. And if we're playing with our little sticks and blocks and everything like that, there's a one carbon unit. And so it's important. So methionine is very important. And so here's what happens. The methionine cycle, what it does is it regenerates the methionine. That's the main pathway for regenerating methionine when there's not enough around, when you're not eating it. So you eat this cheeseburger, which is loaded with methionine. And then over the next hour or two, your liver is busy getting rid of almost all of it. Now that's okay, because now you have this regenerating machinery to remethylate your methionine. Except there's very common mutations. One is called C677T mutation of MTHFR. People who have it and who studied it know what I'm talking about. It's a lot in the popular literature. It's called methionine tetrahydrofolate reductase, which is it's a key step in the remethylation of methionine. And if you have this particular mutant version, when I say a particular version, depending on where you come from in the world, 10% to 20% of the population may have a particular mutation in this gene. So the enzyme doesn't work well. So you're not very good at regenerating methionine. If you take glycine, remember glycine is used to get rid of excess methionine, but if you add more glycine, it doesn't help you get rid of methionine. It doesn't do that. You always have enough glycine to get rid of all the excess methionine your liver has. The trouble is, in between meals, and a lot of people like this, they know they need high protein snacks in between meals because they need to have more methionine. Why? Because your methionine clearance system works just fine, and you have enough glycine to keep that working just fine, but you don't have enough regenerative capacity in between your meals, in between your periods of intake of methionine to keep your methylation high. So you're a low methylator. So what do? You have to have methionine in between meals. So my daughter I never did a genetic test, but I'm pretty sure that she's a low methylator, has all the other kind of signs of it. And what fixes that, and I think her mother did, because what always fixed that, she used to have high protein snacks between meals. So my particular favorite, and that seems to work just fine for my daughter, is Brazil nuts. Brazil nuts are exactly 1% methionine by weight. So instead of taking S-adenylyl methionine as a supplement, you can buy SAMe as a supplement, but that's a little bit like the magnesium glycinate story. SAMe has actually got very little methionine in it. It's mostly adenosine, which you don't need. And so it's a very expensive way you get very little methionine. You want to get methionine? A Brazil nut is about 3 to 5 grams. So if you take 3 Brazil nuts, you're taking 100 milligrams of methionine. That's the best kind of methylation boost supplement, I think, is have 3 Brazil nuts and you have 100 milligrams of methionine. And your body will turn it into SAMe just fine, but SAMe is very inefficient. It's mostly not methionine. And if you're low methylators out there, try the little Brazil nut trick.
I love it.
In between meals, yeah. Have a few,
but no reason
don't have too many, huh?
Yeah, don't have too many. I've read that because
right, because they have selenium in them. And if you make a meal out of Brazil nuts, you may end up with selenium poisoning. You don't want to do that. Yeah. But if you have a few, 2, 3, 4 Brazil nuts in between meals, once or twice a day, that is not going to hurt you at all. And it will give you do need selenium. It's also an essential nutrient. You need selenium, and that's in a very usable organic form. But Brazil nuts are an excellent source of methionine that you can titrate very precisely in between meals if you're a low methylator. See how that works out for you.
Yeah, but you don't think there's a reason to avoid glycine if you're a low meth?
No, not at all. No,
Got it.
because that's just as important.
Yeah.
It's just as important in terms of inflammation and anything else. And as we found out in our own experiments, disproving my initial hypothesis that supplementing with glycine will help to clear methionine, it doesn't.
Yeah.
Doesn't. It just gives you more glycine. And it's hard to, as I say, you can't really poison yourself with glycine.
Yeah.
Not by eating it anyway.
Okay. There's a few more things. Performance. I've seen them give glycine to marathon runners, and it's used for creatine synthesis. So muscle wasting. What do you think of the benefits for those?
Well, two things. Creatine, you will make creatine from it. Yes. And you can increase your capacity to make creatine. All of these, we're talking about these in one way. We talk about, we're not looking to diagnose or treat or cure any disease. This is just normal function. When you start getting into marathon runners, you're not talking about normal function anymore.
So true. That is so
disease,
true.
But it's also not normal function. So you really want to push it when you want to push your body to make more of this or more of that. Yeah, it's a raw material for creatine, but also I think particularly muscle recovery. When you use your muscles and they're sore the next day, that's intramuscular inflammation. And I remember, I'm a snowbird now. I don't live in the winter in the Northeast anymore like I used to. But when I was in my 30s, it was getting to be a chore to be shoveling snow. And then by the time I got into my 50s and 60s, it wasn't a chore anymore because I was eating Sweetener. And so I was not sore the next day. I could shovel lots of snow and the next day I'd be fine.
Isn't that amazing? And I read at least one paper where they attributed this to glycine's benefits for sleep. So if you break down that muscle, it's not only going to help with the inflammation, but also sleep and recovery is a part of
sleep, yeah. One way it can help you sleep if you're not having inflammation, if you're not in pain, you can fall asleep more easily. That's true. But in particular, the glycine receptor was known actually for many years before it was discovered in the 1990s by a group at University of North Carolina. They did most of the work with the glycine receptor, and they proved that it was the same glycine receptor that had been known for decades as a neurotransmitter receptor in the central nervous system. And the central nervous system, the way nerve signals are transmitted, what they call action potentials are transmitted, is through, again, this depolarization. But the switches go on and off very quickly, on and off and on and off and on and off. And it's neurotransmitters that actually effect this. The neurotransmitters that make the depolarization happen help to transmit the impulse. But then there are also a class of neurotransmitters which are inhibitory, which inhibit the transmission of the pulse. And glycine is a key inhibitory transmitter in the central nervous system, so that it actually can, and many people reported, and health food stores used to sell glycine years ago, long before I got onto it, as a way of promoting healthy sleep. And it doesn't make you sleepy.
Yeah.
But if you want to go to sleep, it will help you go to sleep because it is a neurotransmitter, which means it's that same glycine receptor. And this is another case where, again, it's not working to help you sleep at a biochemical level. It's working at this cellular physiological functional level. And one of the things we never got to, by the way, you want to talk about the first step and then the last step in inflammation, right? So glycine is your body's natural anti-inflammatory. It stops the initiation of the inflammatory cascade when it's inappropriate or excessive. But also, and this is a recent discovery, is that glycine is key in the ultimate going nuclear, where the cell just swells up and bursts and releasing inflammatory things all over the place that you get in toxic shock. Now, it was known since the 1980s that it would prevent toxic shock. This is from another scientist named Joel Weinberg in the University of Michigan. Published this in the 1980s. He was working in plant transplants. He was a kidney transplant guy, and he was trying to figure out how to keep kidneys from self-destructing while they were going from the donor to the recipient, because it's very delicate tissue. And it turns out that glycine was the key ingredient. And what it does is it's that very last step where cells they'll swell and they'll develop all these blebs, these outpocketings of fluid, and then burst. And it was thought that, yes, they swell, they take on water because they develop these pores. and then they swell up and they burst. And then it turns out, guess what? They'll swell up, but they won't burst if there's enough glycine around.
Mm.
So glycine actually prevent the very last ultimate step of the inflammatory cascade. That is what kills you in toxic shock. And the very first step in the inflammatory cascade, both regulated by glycines, the alpha and the omega of the innate immune response. That's how fundamental it is. And it's so fundamental, as I say, it's even been made long before any living creatures were made.
Yeah.
It's really the bridge between the organic and the inorganic world. And unfortunately, it's still thought of largely as non-essential, but it is really essential in order to have a properly functioning immune system, which is what's responsible for all the excess inflammation or lack thereof.
Yeah. And one of the papers I really liked recently that I sent to you was, it was an animal model, but they did prevent the development of a cow milk allergy, which I thought was really cool because of allergies and their rising prevalence.
Yeah, when you have actual allergy is another function of the immune system that's like when you have a vaccine or the disease and you make antibodies to the virus or the bacterium, right? A slightly different kind of antibody called IgE is what happens in allergy. And it's down the line of reactions of the immune system to a pathogen, something that generates disease or something which may be harmless. Something is called an allergy when you are developing an immune response, a specific immune response against something that's harmless. That's called allergy. You're not allergic to anthrax. It's something you mount an immune response to. But when you mount an immune response to something that's harmless, that's an allergy, like peanuts, something like that. The initial step in the formation of any immune response, even the delayed immune response, hypersensitivity response, or the antibody response to a disease, the first thing that happens is these macrophages have to go in and gobble up whatever it is they're going to react to. They gobble it up like little amoebas. They go around, they gobble it up. That's the first response. That's what happens before inflammation. Even you get inflammation is if their response is also secreting chemicals, starting that cascade in order to kill something. There's a lot of different mechanisms in the immune system. There's sort of different kinds of guns and artillery and so on. It's fascinating, even if you look at it on a micromolecular scale, how it actually happens that way. Because bacteria, after all, they're cells, and they have a cell wall which protects them from the outside. And if you blow a hole in the cell wall, you kill the bacteria. We have a system called complement, which does that. It actually sets up a structure on the surface of the bacterial cell, and then it pounds a stake right through it and blows up the bacterium. That's called the complement system. But all of these things begin with a macrophage gobbling up something that doesn't belong there. It's a piece of a cell that died, or it's a cell that's something wrong with it, or it's virally infected, or it's some bacteria that got in, or some mold or something. These macrophages are in the blood, they're in the brain, they're in the lungs, they're in the muscles, they're in every organ, has its own resident army of macrophages. So the first thing they have to do is gobble up something. And then once it's gobbled up, internally it's digested. And then the bits and pieces of what was gobbled up are displayed on the cell surface of the macrophage. Then another immune cell comes along and says, that's interesting, that looks dangerous. And it sticks to that, and then it activates another cell which can make antibodies to that substance, or that bacterium, or that virus, or that mold. And in some ways, we don't really understand all of it, but allergy works that way, and it makes a different kind of antibody called IgE as opposed to IgM or IgG, immunoglobulin.
So is glycine somehow changing the presentation?
What glycine does, it prevents the activation of these macrophages.
Yeah.
So it goes back to the initial glycine receptor trigger lock phenomenon, the way that it works, I think, in the whole milk allergy thing. And there was another thing that was important, I think, in another one of these discoveries, like, gee, I wasn't even taking it for that. I wasn't taking sweetamine for any particular reason. And then it had all these benefits of everything from muscle soreness to sunburn and injury, that sort of thing, is that I noticed when I was younger, before I knew about any of this glycine stuff, whenever I go to the dentist, I'd have this It would be this very painful, bloody affair just to clean my teeth.
Yeah.
And I never flossed my teeth. Why? Because I flossed my teeth. It would cut my gums. They would bleed. They would be painful. It was a mess. And then after taking glycine for some time, guess what? All went away.
Mm.
Some of the open sulci are still there, but they've gradually over the years closed up. I get my teeth cleaned. They don't bleed. I don't get any more gingivitis or periodontitis or even cavities for that matter. And there was a study that came out, I think only a year or two ago, only in abstract form, where they were using, in terms of treating implants, dental implants, to keep them clean and to keep them from gum infections around them and so on. They actually have micronized glycine powder that they will actually spray in, because that will keep everything from reacting. It'll prevent inflammation. And that's known now in the heart disease field. They know that if you have a lot of periodontitis, dental infections, that sort of thing, they think it's a way that some of these bacteria may get into the heart and cause endocarditis. I'm not so sure if it's really infection or it's really just inflammation and a glycine deficiency that's manifesting. If it's making a mess in your gums and teeth, why isn't it doing maybe doing the same thing with blood circulation in your pericardium?
Oh, I love that.
I don't know. Some of the answers, we'll still find them out with future research, but it's just amazing how universal and fundamental glycine is as a nutrient.
Yeah, it's incredible. And we're going to move into some Q&As, but I want you to comment on one last thing. And also, we didn't have time to talk about it, but they discovered a new glycine receptor that might be relevant for depression. Glycine is also helpful for neurodegeneration. Even when you don't sleep well enough, there's been studies that show that it improves cognition the next day. But the last thing I want you to comment on, because people were asking about it in the comments, this is, I guess, one of the Q&As, is what are your thoughts on glyphosate? And glycine.
Yeah, that's interesting. That's Dr. Seneff at MIT.
Yes.
It's really amazing that it's really been demonstrated to be such a poison just from the clinical results, just from the people getting poisoned by it. And they keep saying, oh no, this is safe. Glyphosate is a small molecule. It's an herbicide, very effective herbicide. Spray it you don't have to bend down and pluck out that clump of crabgrass. You can just spray a little glyphosate at it, a little Roundup, and take care of it, except that stuff is poison. It's very toxic. One of the main hypotheses that Dr. Seneff has basically promulgated and promoted is the idea that it is mistaken by the body's protein synthetic machinery for glycine. So it's reaching as the protein strands are being generated on these protein knitting machines called ribosomes, and they reach out for these amino acids. You get a glycine here and a cysteine there and a lysine there and a valine there and so on. When it reaches out for a glycine, if there's a lot of glyphosate around, it will actually mistake the glyphosate for glycine and erroneously put in the glyphosate. And so now you have a protein that's not properly put together. It won't function. You'll get all kinds of problems from it. My only issue with that, it's a very good hypothesis, is that it's never been proven. And it's one of those hypotheses that if you have a lab and you can do amino acid analysis, you could take a very simple experiment. You take people who've been exposed to glyphosate, people who've not been exposed to glyphosate, and you take a look at serum albumin, let's say they're the most abundant protein in the serum. You take the protein and you do an amino acid analysis. If there's glyphosate in there, there's less glycine than there should be, and something else that there shouldn't be there, then you have your test of the hypothesis. But I know that Dr. Seneff says that she doesn't have a lab, and she's trying to goad the pharmaceutical industry or the chemical industry, people who make the pesticides, the people who make Roundup, into doing the research. But they may well have already done the research, and it's buried. You don't know. It's really sad how the economic imperatives of things really color how things are marketed and produced.
And it really does, and it is sad.
And not researched the way they should be.
Yep. And we're going to have Dr. Seneff on to talk about that.
Oh, good. Maybe she's got some updates on that, because I think it's actually very, when people talk about science, show me the data. It's all the data. The data is the last thing. Nowadays, they publish so many papers based on, we did our metabolomics and we did our lipomics and our proteomics and our genomics. And we took someone with this kind of disease and someone who doesn't have the disease, and we measured all of the metabolites, we measured all the genes, we measured all the proteins, And we found this and this and that were significantly different because we put it through our computer. And it tells you what's different, but we don't know why. Why? Because it's not hypothesis-based science.
Yes. And
Old days, yeah, they call it hypothesis-based science. The old days, we used to call that science. What they call database science, where you get all the data that you can, thousands and thousands of data points first, and then you go look and you try and see what's going on. We used to call that a fishing expedition.
yeah, it definitely has changed.
That's what it is. Yeah, science largely is these fishing expeditions, and people, you find things that are statistically significant correlations, and you don't know why, and it leads you down a lot of rabbit holes and dead ends, and leads you into thinking about some things which are harmful or not harmful because you're looking at them totally out of context.
Yeah.
Just a data point rather than, I've made these observations and I think this is what's going on. Let's test it and see. That's real science.
Yeah.
And unfortunately, there's less real science and more of this database fishing expedition stuff going on.
Hopefully we can get back to that.
Buy my book.
Yeah,
The
buy his
Glycine
book for
Miracle
sure.
on Amazon, and you can read all about it. I have a couple of chapters on science.
Definitely, like I said, I think it's one of the most important books I've read. Also a Q&A that is really important to get to is glycine is recognized as a key metabolite involved in cancer cell metabolism. So as they said, research shows that rapidly dividing cancer cells have an increased reliance on consuming glycine. So
Sure.
I would just love your comments on that.
Glycine and anything else.
Yeah.
Everything else, because they're growing rapidly and they need more things to grow. So you'll see, like there was a paper came out that said breast cancer. They had they said, oh, so many different cell lines derived from human breast cancers actually have an increased utilization of glycine. Isn't that amazing? So they more efficiently utilize glycine. And we also know from older research, but this is also well known, that many human cancer cells have an absolute requirement for methionine that is they're more dependent on methionine than normal cells. In other words, it's still essential, but remember I talked about all that excess machinery, all that machinery to regenerate and recycle the methionine. You have to look a little bit about cancer evolution, which I also have a chapter about in the book, and that is what makes cancer cells grow in the body. And there's a Darwinian selection process that goes on. And abnormal cells will form, tumor cells will form all the time in a normal body, but your normal immune system will get rid of it. And so what happens that actually makes a tumor ultimately grow into a cancer cell that will become dangerous because it will actually now grow and invade other tissues at the expense of the host? What's the selection going to be based on? A typical body, if we're all mostly glycine deficient, and we have lots of methionine. So the common condition where cancer develops is a body which is glycine poor and methionine rich. So there's lots of methionine. So that will select for a cancer cell that can't recycle methionine. But who needs to recycle methionine? There's always plenty around. It will also select for a cancer cell which can use glycine more efficiently. Why? Because there's so little of it around. Mm-hmm. So the imbalanced dietary regime that we're generally under, the overall in our society these days, has people's bodies being methionine rich and glycine poor, which selects for cancers to develop, which cannot recycle methionine because they don't need to, and which are very good at utilizing glycine because there's not that much of it. So now you say, okay, but now you have a cancer, and the cancer is better at using glycine than the normal cell. And we do our experiments in the tissue culture, and we see, aha, when we add to the culture medium, when we add glycine, the cancer cells grow faster. So isn't it bad if you have a cancer or you might get a cancer? Isn't it bad to take glycine? Not so fast. We have to think about the amounts. You look at those experiments. I challenge you to do it. Go look it up. And you'll see, yes, indeed, you put in 100 micromolar glycine into the culture medium, and these cancer cells will grow faster. So where are you going to find somebody with less than 100 micromolar glycine? Everybody's got at least 100 micromolar glycine.
Yeah.
It's like the old methionine restriction deal. There's always going to be plenty of glycine around to feed a cancer cell or to clear excess methionine. So we're not talking about physiological levels. You take a normal person, there's a person, That's the essence of chemotherapy. Eventually, they starve you to death, is to provide an environment where cells can't grow. Okay, let's have a poison that makes cancer cells not grow as well because it's going to poison dividing cells. Then your ordinary normal cells can't divide either. All I have to say is in terms of supplementation, ask your doctor. Yeah.
Yeah. No, I think
I can't give medical advice. I can just tell you what the science is.
yeah.
And the science is you have a cancer cell. Yes, it's going to be very efficient at utilizing glycine, and it's going to utilize all the glycine you got, whether you have more or not. And if you try to poison yourself so that there's no glycine in your body, people die of chemotherapy, not of cancer for the most part. We know that.
It's complicated.
This is the tough thing is that you develop the cancer is now you want to selectively poison a cancer cell. And if I have this kind of cancer and am I hurting my selective poison, you have to ask your doctor what mix of chemicals are they using to try and kill it. Anyway, will this interfere? I don't know. It may interfere with some chemotherapeutic substances. This is the kind of thing you have to ask the doctor about. I'm about research for how the human body works generally. And it will work for you this way or that way because that's the way it generally works. When you start getting into individual details, especially when it comes to a disease state or something like it, like an extreme athletic state,
Yeah.
where you want to push your body and say, is this good for me? Is that bad for me? Is it good for you to be an Olympic athlete? Probably not. It's probably not healthy to be an Olympic athlete. Look at all the stress. Is it healthy to be a Major League Baseball pitcher? If you don't have Tommy John surgery, you're not going to be successful anyway. So you have to look at athletics, professional or Olympic grade type athletics has to be looked at almost like an oddball sort of disease state. It's not really healthy physiology. You want to know what's generally healthy and how much glycine you generally need and how you can get it and how it works? I'm your guy.
That's right.
I'm not an Olympic trainer and I'm not a doctor. I'm a PhD doctor. I'm not a clinician. That's it.
Perfect. I love that. Yeah, never medical advice. 2 last questions about that type of thing. And then I will let you tell us where we can connect with you. So people are wondering about the difference between L-Glycine, D-Glycine, forms of glycine. What do you think about that?
No, I think about it as that's what happens when a little bit of ignorance comes in.
Ooh.
And you see it all the time. Somebody who doesn't know any better injects something in the information stream of society, and it stays there forever. L-Glycine. Lots of people sell L-Glycine. There's no such thing. Glycine is not chiral. Glycine, there's no left-handed glycine and right-handed glycine like for all the other amino acids. Threonine and lysine and valine and isoleucine, there's all L amino acids are the ones that are physiological and natural, whereas the D ones or the mixture of D and L are made by physical non-living processes. Glycine is glycine, period. There's no L, there's no D. If they sell you L-glycine, it's glycine. I'm assuming it's glycine. But that's just ignorance of chemistry.
Okay, last one. TMG. Can you take TMG?
Well, it's not the same thing. You can make glycine from TMG, but you make glycine from TMG by taking off its methyl groups and using the methyl groups. So TMG is a good source of methyl groups, but it's not a very efficient way to get glycine. In fact, it will add to your methylation load. Now, I'm not familiar with a lot of the literature about TMG, but generally that's what it does. It can be turned into glycine by demethylating and taking off those methyl groups. Remember, there's that sophisticated machinery for remethylating methionine because that's essential. You can get methyl groups off of TMG that can actually remethylate methionine eventually. There is that machinery, but it's not a good way if you just want the benefits of glycine, just glycine. It really makes it a different substance altogether.
Perfect. And I had someone write this interesting comment that I wanted to just mention is there was a carnivore listener who said they believe there was a theory that too many omega-6 seed oils could lead to sunburn, but he was wondering maybe it's the glycine. Maybe if you're eating the whole animal and the glycine is preventing that inflammation, maybe that's the reason. Yeah.
If you have too much omega-6 oil and you have a sunburn, it could make it worse because the omega-6 oils generate the prostaglandins, which there's two kinds of prostaglandins, those which amplify the inflammatory message and those which
Dampen.
inhibit the inflammatory message. And the prostaglandins from omega-3s are the inhibitor kinds, and the prostaglandins from omega-6 oils. So if you have a lot of omega-6 oils, you'll get more of the inflammatory, the pro-inflammatory. So it could make sunburn worse because whatever inflammation you have, even though you shouldn't have it because you don't have enough glycine, it can make it worse if you have omega-6. So it's not, there is a place where that thinking fits in. It does have something to do with it. It does play a role in that way.
Okay, Dr. Brind, there's more questions, but we've done a great job today. Thank you so much for getting.
We'll do it next time then. We'll have to have
We'll
another.
do, yeah, we can keep this train going, but can you tell people, like I said, glycine, we do this podcast because we think there's a widespread deficiency and there are many ways to get it. But Dr. Brind and we both created products that make it easy, like our bone broth protein powder. Also, tell us about Sweetamine.
Sweetamine is just straight glycine with a little, to make it taste a little more like sugar. Yeah. But it's basically a glycine supplement. And I started doing that. I started this company to make it called Natural Food Science. And I started it as a business, not because I'm a businessman. I've always been a scientist and a professor. But when I was 60 years old, I thought, hey, this discovery is something which people need to be able to have available. Yeah. Because if I just stick to my papers in my ivory tower and arguing with other academics, I may be long gone before anybody knows about it. So once I discovered how important glycine was, how safe glycine was, how easy and obtainable it is, how simple it is to take, and how enormously beneficial it is to so many people, I started a company just to make it available. And it's not expensive. Most of my customers don't pay more than about $1 a day, a daily serving. It's 8 grams per serving of Sweetamine. It also has taurine in it, which is also a very good amino acid. Lots of benefits we don't have time to talk about today. But that's it. You can just go to sweetamine.com, SWEETAMINE.com, sweetamine.com. And there I'll particularly point you not only to the buy now page, but also check out the testimonials page because it has a searchable box in there and you can punch out any symptom or disease or whatever you want, any kind of condition, just type it in there. And if anyone has written a testimonial that it has helped them with that condition, it will pop up. So it's informative that way if you want to know will it help with my this or will it help with my that. Again, it's not meant to cure, diagnose, treat, or any disease, but a lot of diseases are a lot worse without it. I had one testimonial from a fellow who had a case of shingles, and it was the shingles in his left lower back, and it was giving him pain in his hip that was absolutely unbearable, and absolutely nothing worked for the pain until he tried Sweetamine because it was inflammation. And that's another thing I discovered because that's what happened while I was taking it's an ongoing experiment in a sense. Seeing what would happen if you had it and if you don't have it, is that I got shingles. See, so glycine doesn't prevent shingles. One day I woke up, it was 2015, so I had been selling Sweetamine for 3 or 4 years. I'd been taking it every day religiously and some glycine before that. Didn't prevent me from getting shingles. At the age of, how old was I? I guess I was 64. And it was a typical rash in the lower back. And I had a little bit of malaise and just generally didn't feel 100%. But otherwise, I had that characteristic rash. So I went to a friend of mine who was a neurologist. He said, yep, I confirm your diagnosis. You have shingles. It's classic. This is the classic shingles rash. And it was classic in every other way. Except guess what? The rash was totally painless. I found it only because I was soaping up in the shower and I thought, what are these bumps I feel on my fingertips? And I got another mirror to it and gee, that looks like a shingles rash, a unilateral characteristic rash, and that's what it was. And now I had other confirmation from other people with shingles is that one of the things that makes shingles really painful, which is the reason why people get immunized against shingles, because they don't want to catch it because it's like your skin is on fire, they say. They say, to me, it was just a rash that took several weeks to go away. But so it makes that rash was painless. So It's not meant to diagnose or treat any disease in the sense, but the symptoms of some of these diseases are horrendous, and they may only be horrendous because of secondary inflammation
Mm.
that happens. The gout is another one of these things. It's secondary inflammation from the injury that's caused when the uric acid crystals or gas or an outbreak or a breakout, whatever they call it, when you have a gout crisis.
Yeah.
Very helpful for all of these conditions because it prevents inflammation, including the secondary inflammation that follows some of these diseases. So pain's not a disease, and it helps a lot of that.
Yeah, and I highly recommend you check it out. And even just from the first podcast, there's been so many people who've given testimonials about I'm using glycine for this. And it's actually quite inspiring that something so simple and often overlooked could be that
Yeah, I was
powerful.
inspired enough to actually make a business out of it because that
Yeah.
way it's available. And the more I sell, the more I talk about it. And thank you very much for the opportunity, the big megaphone that you have to enable me to talk about this and all the other aspects of science that I'm familiar with. And I try to answer as many of those comments as I can, but I think there were almost 2,000 of them from the last podcast.
Yeah, there's a lot
I
of
thank you for filtering them down into a reasonable number of merely dozens, and that I can actually, and I'm sure there will be more, and I'll be happy to take a crack at them. Always something new.
Yeah, I'm saying usually, like you were saying, 15 years for academia to penetrate the mainstream, and so you're just such a wealth of information. So I do want to have you back because taurine also very fascinating.
Yeah.
Would love to learn more. But for today, I think we'll just let that be enough. And do you have any famous last words or anything you need to make this conversation feel complete? Or are we good?
We're good. I would only be repeating what I was saying, but
Yeah,
don't forget
trisomy.
that's my brand of it. But get however you get your glycine, whether from sweetamine, from bone broth, from anybody else's formulation of glycine, just make sure you get enough glycine. It really is good science.
Dr. Brind.
Make sure you get enough because it really is an essential amino acid that